Alrighty, welcome back to 105. Thank you for joining me today. So today we are talking about pointers, which if you have some cursory knowledge of a programming language before, like Java or Python, this is where things start to diverge a little bit. And pointers are generally considered the first hard thing about C. That takes a little bit of practice and knowledge to get over. So, it was no mistake that all the way back in lecture 1, I discussed how we represent numbers in binary. So, recall if we have some larger value, like we have a 64-bit number, which again, just remember, this will come up forever and ever and ever. If you are doing programming, there are 8 bits to a byte. So 64 bits is the same as 8 byte. They are equivalent. And if I was to represent that as a whole number using, using the twos columns for everything, well, it would be a lot of digits I have to write. In fact, I have to write 64 ones or zeros. And then the value of the first column here would be the ones column, then the twos, then the fours, and then up to some gigantic number. So if I just wrote this where all of these represented 0 and this was my number in binary, what would this number be in decimal? So just a whole bunch of zeros, then 1, 0, 1. Any guesses? Yeah, 5, right? We just add all the columns just like you did before, where you had, the digit in the tens column, the ones column, the hundreds column, and you just added them all together. The only difference is in this case, your columns are powers of 2 instead of powers of 10. So this would just be in decimal 1, and then 0 times all the other columns are 0. This is in the fours column, so there's 1, 4, and then 1, 1. So in total, this number would be a 5 if we translated it back to decimal. So everyone clear on this again before we get weird? All right, so binary numbers, too long to write out by hand. So everyone has a 64-bit CPU on their machine. If you want to, write a number in such a way that a computer can understand, writing 64 ones and zeros is going to be a pain in the butt. We can't quite use decimal numbers, they're for humans, but computers are based off powers of 2. So it turns out that it is very useful to use a base 16 to represent numbers that computer uses instead of base 2 or base 12, or sorry, base 10. So you might be thinking, oh, well, if I have base 16, I only have 10 digits, so where the hell do I represent the other other digits? So decimal, again, uses 0 through 9 as a digit. Binary uses a bit, 1 or 0. And base 16, what it does is, well, we need 16 different characters to represent each number, 0 through 15. So we borrow 0 through 9 from the digits, and we need 6 other characters to represent 10, 11, 12, so on and so forth. Yep?
Why is base 16 more convenient?
So base 16 is more convenient because if you do the groupings, each base 16 character represents 4 bytes, or sorry, 4 bits. So we can write 4 times less characters to represent the same thing. So we only need to write 16 hex characters to represent a 64-bit number. So yeah, the reason why it's more convenient is because it kind of keeps it in powers of 2 that computers like, but I don't have to write as many characters at once. So let's see what that looks like. So to actually represent the values 10 through 15, we just borrow letters to represent their values. So 10, well, we want to transform that into a hex digit, or hexit, whatever you want to call it. So 10 is A, 11 is B, and it's just alphabetical. So 12 is C, 13 is D, 14 is E, 15 is F. So long form, You can call it a hexadecimal digit or hexet. No one really calls it a hexet. Some people just call it, just say hex. It's just a hex number, and that can be any number represented by one or more hexits. But that is technically, each character is a hexet. That represents the value 0 through 15 if we're doing base 16. So in C, if you want to write hex, which is again short for a hexadecimal number, you can start that number or start that literal with the prefix 0x. And then after that, you can write your value in hex characters. So you're allowed to write the values 0 through 9 and then A, B, C, D, E, F. So this is not testable, but it will help you understand computers because, as we know, we have to discuss a bit about memory. So same rules apply as in base 2 or base 10. It's just we have a different base. And this is convenient because, like was asked before, each hex digit represents 4 bits. So it's easy to go back and forth between binary and hex. And that's what computers like. Computers like base 2. So they typically only show decimal numbers for you and for us humans. So works well with bytes as well because 2 hex digits represents 8 bits or exactly 1 byte. So if I gave you the hex number, all zeros, and then F4, what decimal number would that be? Well, same rules apply, just my columns are different. So 16 to the power of 0, always the ones column. So it's going to be whatever the rest of the number is plus 4. And then this 16 to the power of 1 is the 16s column. And F represents the decimal number 15, right? So in order to translate this back into decimal, it would be 15, so the value of F, times the column, so 16. So 15 times 16 plus 4. So if we do that, this number would represent the decimal number 244. So anyone have questions about that? Same idea. It will come up in later courses. Again, won't have to be testable for this, but we'll see some hex today because, again, that's how computers represent information, just using bytes or bits. All right, so all the way back in lecture 2, I said an address contains a byte value. So in here, all of the values stored at a particular address represent a byte. So the value is in the blue box where I have the address below. So you have a lot of memory on your machine, and each of them are given an address or just a number to identify which byte is which. So you have a lot of memory. This address might be 512,000, and then the next one would be 512,001, so on and so forth, kind of like just a street number where they all live on the same street, and there's an individual value stored there. So if each value contains a byte or 8 bits, it could represent any decimal number between 0 and 255. So how we actually represent memory addresses is because we're using computers, we represent them in hex. So in the previous slide, I showed the addresses as decimal numbers. If I was to write them in hex, which would be prefixed with 0x, I could write them as follows. It would just be 7D000, and then they would go up by 1 each time. But these numbers, if you draw out the columns and all that stuff and calculated them back, you would get the exact same numbers as we had before. We're just representing them with a different base. So everyone okay with that? Again, those are just numbers. It's just numbers computers tend to like better because, again, computers only deal with bits 1 or 0. Yep.
Wait, so just to confirm, the value in the blue boxes, are they the value of like a variable, and then the number below is the address that value is assigned to?
Yep. So in memory, right, memory is just a bunch of bytes, and that information has to be stored somewhere in memory. And the values stored in memory would be, yeah, like the value of variables. So this could be the, C keeps track of, luckily, we don't have to use these addresses directly. C keeps track of them for us. So it would know the variable x lives at that address, for instance, and then has this value. All right, any other questions? Yep. So in hex, yeah, the question is, in hex, how would you represent a negative number? So for this, how we're just doing it in hex is just representing 64 bits. We just want 1 or 0 for all of them. If we want, and that's all we care about, just 1s or 0s, 64 of them. And then if we want to do some encoding to represent negative numbers, that depends how we want to do that. There's lots of different ways to do that. So you'll see some options in later courses. But for now, even to represent negative numbers, it will be some sequence of 1s and 0s because that's all we got. And we have to decide which 1s and 0s represent negative numbers. Just like for characters, we have to decide what 1s and 0s represent, like an A and things like that. So you'll see that in 243 in the second semester. All right, any other questions? All right, cool. So again, C stores the value of like int x. If I have a variable int x somewhere in memory, technically int x, an int, requires 4 bytes, right? So we could, somewhere in memory, let's say the value of x is stored at this address, so it consumes these 4 bytes or these 4 addresses. So it would start at this address, 7D004, and it would take up 4 bytes in total. So the blue box would represent the value of x, and since it is an integer, it could be a larger value than just a single byte, right? We're just grouping 4 bytes together and interpreting them as some bigger number than just a single byte at a time. So everyone okay with that? And of course, for a double, it'd be 8, and then the encoding is quite involved. So a pointer, and this is going to be very important because we're talking about pointers now, is the starting address of that value in memory. So that int x from before, that takes 4 bytes all in a row. And always for variables and things on computers, all of, if we say something is 4 bytes large, that will always be 4 byte addresses, all sequential, all in a row. So since we know that and that's our rule, then whenever we say a pointer, it's the starting address of a value in memory. It is the first byte, and we know if it's an integer, we have to read 4 bytes starting at that address. So this is exactly what that ampersand operator does. So that, again, is the address of operator, and its result is a pointer to that value. So for values that take up multiple bytes, it's always the lowest address, or the first byte. So in the previous example, to understand what happens or what gets returned if we do ampersand x, in this case, if x spans these addresses in memory, if we ask for the address of x, we will get this value. So it will be 7D004. So everyone okay with that? And we don't need to know why it's 7D004. C just does that for us. Yep. Yeah, and also we'll get to that in a second. So the question is, in this case, is the pointer its own type? And yes, it is. So there is a special type for pointers. We kind of saw that before, but we'll go into it more today. But any questions about that? So the address of x in that example would be 7D004 in hex. Again, I just kind of made up that number. All right. So yeah, here's the next slide. Pointers are a new type. So assume we have int x equals 1. So that variable x will live somewhere in memory. It will consume 4 bytes, and it has the value 1. So when we do equals 1, that means we set the value of x to 1. So if I have some variable called int z, and I try and do like assign the value ampersand x to it, well, my compiler is not going to like me because the type of ampersand x is actually int star. So int star means it's pointing to an integer. It is not an integer. And anytime you see the star, star is just another way to say it's the address. So this is an address, and at that address is an integer. So typically we don't like saying addresses, but they're equivalent. Typically we say it's a pointer. So it's a pointer to an integer value is another way to say that. So each time you take the address of a variable, the way to remember it is you just add a star to its type. So if I have, again, x equals 1, and then I do ampersand x, the type of this expression is int star because I took the address of x. So since I need my types to match, go away. Since I need my types to match, I can declare a new variable called z, and the type of that would be int star z. And the star I can place with the int or after the int. Doesn't matter where you place the star. It's kind of a style thing, but I'm allowed to do this. And to make it even more complicated, we won't have to do this quite yet, but if I do ampersand z, so the type of z right now is int star. So if I do ampersand z, the resulting type is int star star, which, again, you don't have to worry about it, but it is a pointer to an integer, which is real fun. So let's just ignore that for now, and just note that you can only take the address of a variable. So a variable, by definition, stores a value somewhere in memory, and the value itself might never be in memory. So for instance, if I have, int x1, it means the variable x is somewhere in memory, but that value 1 is not in memory. It doesn't have to be. So I can do something, try and do something silly, like, I don't know, maybe I make an int star y and try and do something like it's equal to ampersand 1. If I do something like that, we already notice the red underscore, and if you do this, you will get one of the worst compiler messages for beginners that I have ever seen. So if you do this, the underline says, cannot take the address of an R value of type int, which should sound like gibberish to you. You will only know what that means when you take the compiler course in 4th year. So what that means in English is basically you cannot take the address of a value. So you cannot take the address of a value or any literal or anything like that. It has to be a variable of type int, not a literal. That's what it's supposed to say. This is, yeah, again, a bad compiler message that kind of like uses very compiler-centric terms. So this basically means you just can't take the address of a value. So I am allowed to do something like this, though, where I just take the address of x instead, because that's a value, and I just get a compiler warning that I have an unused variable. Yep?
So in that line, are you taking the starting address of x and putting it in the address of y?
Yeah, so in this case, I'm creating a variable called y, which its type is a pointer or an address to an integer, and then this would assign the address of x, which would be like, like some big hex number that represents an address, to the variable y.
And y is now that big number.
Yeah, and y is now that big number. So in the case before where we had the example where, whoops, x was somewhere in memory, it would be, in this case, 7D004 would be that value stored in y. Yep.
Why do we need Unported? Like when we say scanf,
Yep.
But when we print it out, we don't need an variable.
Yeah.
So why do we need a pointer for one?
Yeah, so the question is, when I use scanf, I have to give it the pointer to my value, and when I print it, I can just use the value directly, right? So why is that? Well, we'll see an example later, but you want scanf to change the value for you, right? And C is always passed by value. So if you just give it a copy of the value of your X, it won't be able to change the actual value, right? It just gets a copy of it, it would change it locally, and it's gone by the time the function is gone. So you have to give it the address of, so it can point and like change the actual value that it's pointing to. And then when it gets back to your function, you still have that variable, so you can still access its value directly. And we'll have an example of it to make it clear too. Yep.
Do pointers also work for other variable types, or is it just int?
Yeah, the question is, do pointers work for other variable types, or is it just int? And the answer to that is you can have a pointer to any variable type you want. So you could have a pointer to a double, pointer to a char, pointer to a bool. You can have a pointer to any type. In fact, as we'll see in a bit, you can even have a pointer to a void. So what does that mean? So let's see when we get there. So here's that example I just went over. You can only take the address of a variable. And the flip side of that, so there's that ampersand operator to take the address of. So there's another operator we have to be introduced to, just called the star operator. How we say it is it's the dereference operator. It's like how you access a value through a pointer. So if we assume we have, again, x equals 1, and then we have the variable z equals to the address of x, we can do something like int y equals dereference x. And then after that statement, x or y will be equal to 1. So how that works is, well, x is equal to 1. The value stored in x is 1. Then we will get the address of x into the variable called z, which is a pointer to an integer. So if we dereference that pointer, so if we do the star operator on z, you can think of it as it just removes a star from the type. So the resulting type would be, this star removed, so it would be an integer. So we would get back the value that z is pointing to, in which case it was pointing to the same thing that x is pointing to. So we would read the value 1 here. So y would be equal to 1. So accessing a value through a pointer, again, the term we use is it's called dereferencing. So in the code above, I would say to get the value of y, I dereference z. So we'll see an example of that as well in a diagram that will hopefully make it more digestible. So again, each use of that star operator basically removes a star from the result type. So if I have the variable, a confusing variable like a pointer to a pointer where it's like int star star z, the type of dereferencing z in this case will remove a single star. So the resulting type would just be a pointer to an int, is a way to think about it. So here is that diagram to show that, hey, I can actually change the value of variables through pointers without directly changing the value of x. So here is that, I'll show all of the variables and everything like that. So like I showed in the last lecture, was not a mistake, where we have a new scope for main. So I write main and then the green line, and then we will step through it line by line. Now the yellow arrow actually points to the right thing, and I fixed the previous slide as well. So we'll step by it line by line, create variables, and we'll represent pointers as just arrows. So let's see what this does. So if I execute the first line, I create a variable called x with the value 1, right? Just like before. So the only thing that's important here is the value of x. This is just the name for it that we're using in our program, but C is taking care of all that for us. It's just to refer to that value. So everyone okay with the first line? Nothing new so far, right? So then we have int y equals 2. So same thing, we'll create a variable called y. It will have that value 2. Now, when we create a variable called z, which is a pointer to an int, and its value is the address of x. Why we like calling them pointers is because we can represent it like this. So we know that if the type is a pointer, it's an address somewhere. Most of the time, we don't care what the literal address is. It's going to be a big random, essentially a big random hex number we don't care about. C is keeping track of it for us. So when we represent it, we know that the value is actually an address of it's actually an address, but we don't care. We care what value it's pointing to. So in this case, I would represent it as just an arrow pointing to the value x. So it's pointing to some integer. So this is an integer. This is an address. So now I'm pointing to this x. So everyone okay with that? So z pointing to x, the value x. And it should all make sense that the type of z is actually storing a value 2. That value is an address because it's a star, so that value is an address. I don't really care what the value of the address is. I just know that it refers to the starting location of the variable x somewhere in memory. Okay, so now if I do dereference z and assign that value to 3, that dereference operator, remember, if I do z equals something, that would change this value, so it would change the address to something, probably not what I want to do. If you're starting to change addresses, probably something weird's going to happen. So dereferencing z means I'm basically following the pointer one step. So if I dereference z, it means I'm referring to this value. So I'm referring to this value 1. And when I do an assignment, it just changes that value to whatever I'm assigning to it. So it changes that value to 3. So it would change this x to the value of x from 1 to a 3. So now, after that line executes, the value of x is going to be 3. Everyone okay with that? Yeah.
On the previous slide, you put in star star z, and then the type of star z is in star. Could you explain?
So on the previous slide, so if I go back here. Yeah, so it's basically just to illustrate what dereferencing does. So this is like, if my type is int star star z, that means it's a pointer to a pointer. And if I dereference z, the result is just a pointer to an integer. So it just removes one step. So it gets confusing if it's pointer to a pointer. Usually, for now, it'll just be a pointer to a one thing. So if I just dereference it once, I get the result is an integer value. Yeah?
So if you simply said the line like x equals 4.
Yep.
So in this, like, x is assigned in int, right? But
Yep.
like, is it implicitly like pointing to the value at x and changing it? Like
So-
if z, I can imagine like z is like an arrow, right? Where the address of x is in memory.
Mm-hmm.
And like when you just say x equals 3, like what happens?
So when I just say x equals 3, then it means I'm just changing this value of x. And C is taking care of it for us, because x is going to exist somewhere in memory, but it's just changing the value of it for us. So for
It just encodes like its location.
yeah, C keeps track of where all your variables are and everything. So x will exist somewhere in memory by definition, but the nice thing about C is if you just use normal variables, you don't actually care, unless you're using pointers, you don't care where x is in memory, right? You only care about the value. And C takes care of the rest of the details for you. Yeah?
When you use star, it's called like dereferencing. What's it called when you use like ampersand?
When it's using ampersand, it's usually just address. Take the address of it. No one calls it like referencing or anything like that. Yeah, it's just taking the address of. Yep.
So to declare an address of variable, you would have to do the variable type in a star, but then, like, let's say we wanted to get the address of z,
Yeah, so if I, again, this will be slightly above. If I wanted to, take the address of Z, well, the type of Z is int star, and if I do an ampersand, it basically adds another star to the type. So the resulting type is going to be int star star. So I would have to call it something like int star star, I don't know, ZZ, something like that, and that compiles fine. So if I compile that, it'll just say unused variable, that will be fine. If I get rid of it, get rid of a star, I'll get some bad warnings where incompatible pointer types. So it says initializing int star, so that means ZZ's an int star, with the expression of int star star. So the result of ampersand Z is int star star. So if you get compiler warnings where it's like incompatible pointer types, that's probably bad.
Okay, so if you do ampersand and star are like basically inverses?
Yeah, ampersand and star are basically inverses of each other. So ampersand adds a star to the type. The star operator removes a star from the type. Yeah.
So if you dereference like int star star ZZ, right?
Sorry, if I went int
Yeah, star star ZZ.
equals like that, whoops.
No, like yeah, okay, so that's new variable. And then you say like star ZZ equals,
Stars.
like can you change the address? If I say like,
Yeah, so if I create, so if I do this, yeah, I can totally do something like that. It's not special. Like, I can change the value of star ZZ to be the address of something else. You're totally allowed to do that. It just looks really ugly, and you really don't want to do that unless you have a reason to, which you won't have a reason until the end of the course. So we're only going to use one pointer for quite a while.
can you like manually input an address? Like just type in that number?
Yeah, so the question is, can you just manually input a number? So I basically know that, the address of X will just be some big random value. The question is, can I just assign X to some random value, or Z to some random value? So we could just do, I don't know. So if we do that, it'll probably complain that we're not using the right type. So it says incompatible type integer to pointer, but it's C. I can just say, hey, interpret this number as a pointer if I want. So I could typecast it like that. And you're totally allowed to do that. That means I just picked a random address. It's probably not valid. So this is going to be one of the banes of our existence. So if I try and print off, well, if I print off Z, I'll show you how to print off pointer values in a bit. But if I try and dereference Z, so like get the value Z is pointing to, I'm just pointing to some random memory and trying to read it. So if I do that, compiles fine. If I actually run it, I'll see this error message you will see a lot. It will say, terminated by sigv address boundary error, or some type of error. Basically means that's invalid memory. I'm not allowed to access it, and your operating system will just end your program if you try and do that. So if you get into, writing exploits and stuff, you can guess addresses for stuff and modify things you shouldn't, but that's a security course. Yeah?
Sorry, just to add on, like so when you declare Z, you declare it as int star.
Yep.
You have to like say, okay, I'm not looking at OXFF as a number, I'm looking at it as a random address, right?
Yeah.
But then when you print it, you print out percentage D, which is an integer.
Yeah, so like ampersand, or not ampersand, star Z is an integer, so it's trying to get that value.
So would it print it out as base 10?
Yeah, so it tries to print out base 10, but it got this invalid. Yeah, if it was valid, yeah. Because everything is just ones and zeros, it's just how we interpret them. We can interpret it as a number, a character, whatever. But at the end of the day, it lives somewhere in memory. It is a byte of something. All right, so let's go through. So we're having fun. So yeah, and again, during that example, I was able to change the value of X without actually, doing X equals something, right? I changed it through a pointer, which is basically how your scanf works. So if I was to show how scanf works through a function, I can use this example. So same thing, functions can change variables through pointers. So how this works, again, we start executing in main. So if we start executing in main, we create a variable called x, its value is 1, create a variable called y, its value is 2, then create a variable called z, which is a pointer to the address of x, or we just say it's a pointer to x. So z is going to be an address pointing to the value of x. And then if we do call this function set3, again, see the arguments are only passed by value. It just so happens now, in this case, my value is a pointer, which is just an address. So when I call the set3 function, again, it will be a new scope. We're calling the set3 function, and it gets a copy of the argument. So right now, z is some address pointing to x. So when I call set3 and I copy the value to its p argument, well, p is also going to be an address, and since it's a copy of z, the address of z and the address of p will be exactly the same. They're copies of each other. And in other words, it means they point to the same thing. So they both point to x in this case for this function call of set3. And then in set3, I do star p, so I dereference p. So I'm essentially taking a hop to get to the value p points at, which is this value stored here, which is currently 1, and I'm going to change it to a 3. So now I change it to a 3, my function ends, and I come back, and now I have changed main's value of x from another function. So this is basically what your scanf is doing, right? So scanf, the reason we had to do ampersand x, because it's changing the value that's declared in main. Everything is copied by value. In C, very simple language, so I have to have it copy the address, not the value. Everyone get that? Yeah.
So you're putting in the address, like in C, the function,
Yep.
and then you're assigning the value of the address to 3.
So I'm not assigning the value of that address to 3. I'm dereferencing, so I'm accessing the value pointing to that address points to. So anytime you see this dereference thing here, this star p, you basically take a hop. So I hop, I'm actually modifying this. So I'm modifying this value. It's an integer. All the types should kind of make sense. So I'm modifying this integer from a 1 to a 3. Yeah?
Is it possible for you to like declare an integer like x and then like somehow find a way like to not reference it? Is there a way like a number could be like lost?
Is there a way a number can be lost?
No way to access it.
Like no way to access it in a function?
So like nothing that points to it.
Nothing that points to it. You can lose it once we get into different memory allocation stuff, but right now we can't lose it because it has to be declared in a function. So it will always exist in that function, and then after that function it doesn't exist, but it gets cleaned up properly. Yeah?
Can you explain again why x is not, there isn't a pass by value of x, it's just of z when you go into the function?
So the question is, why isn't x passed by value here?
Like you know how you copy the value when you go into a function? Why
Yeah.
does that happen with x? Because you're pointing to x, so then it's like,
Yeah, but what I'm copying, I'm copying the argument for the function. I just always copy the arguments to the function call. So in this case, what I'm copying is z, not x. And z is an address, so that's why these two are exactly the same. So here, like, if I was to draw this out, like this big number, this address would be the exact same number, but it's easier just to represent as pointing to the same thing. Does that answer? Yeah, okay. All right, so having fun with pointers. All right, so if we wanted to, we could print the address of a pointer. That's another format specifier, probably one that's not terribly useful for you. But if you want to print a value of a pointer, the format specifier is &p, and it expects a type of void star. What the hell is a void star? Void star is basically C saying it is just a generic pointer. It doesn't care what value it's actually pointing to. It only cares about the star part, which is an address. It doesn't know what it's pointing to, what type it's pointing to, how many bytes it is. It's just a very generic term that says it's an address to what? I don't know. That's the way C does it. So it's just an address. You don't know what the type is it's pointing to. So the rule is you can't dereference a void star. If you dereference it, that means you get rid of this star, which means you get a void, which means nothing. So it doesn't make any sense. So the other rule is you're allowed to cast any pointer of any type to a void star. So if I have an int star, so something that points to an int, I can cast it to a void star, which is just an address of I don't know what it points to. So you're basically losing information going that way, but you can always do it. So if I wanted to, I could add print statements to verify all my addresses make sense and everything is passed by value. So here, let's see that example. So it's going to be, it's going to be the exact same example, except I'm going to print off the addresses of things. So here, right after I declare x and y, I will print off the x, print off its address in the first thing, and then its value. Whoops, you can't see what I'm doing. All right, sorry. So same program as before. I'll declare an x, y, and a z, which will be the address of x. So here I'll print off x and x's address. So again, our format specifiers are lining up with our types. So this %p is going to be the address of x. I have to cast it to a void star, so C doesn't get mad at me. And then I do equal its value. Then y, wherever its address is, and then its value, so its value should be 2. Then I do set3 with z, which should be the same thing as &y, doesn't really matter. Then in set3, I print off p's address. So p's address, if I do &p, well, that variable p that stores a pointer, that has to be somewhere in memory too. So that type is going to be technically a pointer to a pointer. I don't really use it like that, but it has to exist somewhere in memory. So in our case, pointers are 8 bytes, so it has 8 bytes somewhere in memory. Yeah?
So can you clarify like what the void star has? Like why is it necessary?
So the void star is necessary to print the pointer type because it only cares that it's an address. The format specifier just wants an address. It doesn't care what it's pointing to.
So when you say and x, is that not the address of x?
And x? Yeah, ampersand x is the address of x. So in this case, the type of ampersand x is int star, and I'm allowed to cast it to a void star because having a star just means it's an address. So if I want to use the format p specifier, it just has to be to a generic address. It doesn't care what it points to.
Also, this all care about the type.
Yeah, it doesn't care about the type. Yeah, up.
So why do you need to change it into a pointer to void?
So the question is, why do I change it into the pointer of void? And the answer to that is because that %p format specifier requires a void star as its type, just like %d requires an int. It's just a generic way to print an address. Yeah?
But if both void star and int star just point to addresses, how is their type any different?
If they just point to addresses, yeah, their type's not different. It's the same. But if I want to print it, I just have to print a generic address. I don't care what it's pointing to. It's just the weird rules of C. So here, printing the addresses, then I call set3. I print the address of p and its value, and then I print off whatever the value of dereferencing P is, and then I change it. Then after I print off the addresses of X and its value, and then Y and its value. So if I execute this program, everything should kind of jive. Might be slightly confusing at first, so it's just called, build print. So if I do that, remember our addresses are going to be some large value. So X lives somewhere in memory. In this case, it's like FFFFCC, whatever, who cares? It's just some big, big number. And its value is 1. Y lives somewhere else in memory. Its value is 2. Then P, well, it lives somewhere in memory. Again, I don't have to care. But its value is what gets copied when I call the function. So the first time I call it with Z, and the value of Z is &x. So we'll see that, hey, these two are exactly the same. So the address of X, which is this, is the same value that gets copied into P. So that makes sense. They're the exact same value, so these always have to match. And I see, before I change it, if I dereference it, its value is 1, because that's what X's value was. If I call it again, in this case, P lives at the same address as the first P when I called the function. Doesn't have to, but in this case it will, for reasons you'll again discover in 243. But now the address that gets copied is the address of Y. So this matches this. Dereference it, Y is equal to 2. And then again, the address of X and Y don't change, but their values change at the end. So questions about that? Everything kind of jives, right? So if I go back, just to verify, everything that should match is in red. So, well, all the colors that should match are the same colors, sorry. So the address of X is in red, so it should match the first value of P, so these two match. The address of Y is in light blue, so it should match the second argument of P. And again, the address of X and Y don't change in the main function, so they stay the same. It so happened, again, that the addresses of P's for both function calls were the same, but they did not have to be. All right, any questions about that? Again, you won't be tested on this. It's just showing the values. Yeah?
Can you go back to
The
the code for a second?
code, yep.
On that first print line, like the percent piece that's being printed is from asking the address of X with void, right?
Yeah.
So how does you have &x, which is the address of X, right?
Yeah.
And then passing that to void.
So I'm taking &x, that's a pointer to an int, and then I'm casting it to just a generic pointer, which is just void star.
So how do I still print the correct address for X?
So yeah, the question is, why does it still print the correct address for X? Because it's just generic, like int star says the value is an address, and what it's pointing to is an integer. But in order to print the address, you don't care what it's pointing to, right? So void star just means it's an address. I don't really care what it's pointing to. So the address is going to be the same no matter what type it points to. So yeah, it's just C's way of representing a generic address. If I didn't put this, I'd probably just get a compiler warning. Yeah, so if I didn't do that, I'd just get a compiler warning that says the format specifier wants a void star, but the argument has an int star. But I can cast any pointer to a void star. It's just saying address, I don't care what it points to. Just give me the value. All right, so just before we leave, when I stepped through the code and went through what was pointed to what and what changed, you should be able to do the exact same thing with this swap example we saw last time. So make sure you can step through this, write out the variables in main, do the function called the swap, use the pointer, see what it's pointing to, and verify that the correct things change. So with that, I will let you go, and just remember, pulling for you.